Welcome to the deep dive. If you are joining us today, you know our mission. We basically take a massive stack of sources, articles, research papers, your own notes, and we extract the absolute most important insights, just to keep you ahead of the curve.
Right, getting right to the core of it.
Exactly. And today we are exploring some foundational, true state-of-the-art generative AI research. Our primary source material is this incredibly fascinating paper out of MIT and Stanford.
Oh, yeah. This one is great.
It really is. It's titled Peak Context Map as an Orientation Cache for Long Context LLM Agents.
Which, I know is a super dense title.
Yeah.
But the problem it solves is something anyone who uses AI will just instantly recognize.
Absolutely. To understand why this paper is such a breakthrough, I want you to imagine hiring, a brilliant enterprise data analyst.
Okay, I'm picturing it.
So you sit them down in front of a massive database. Let's say it's a 50,000 entry customer feedback corpus for your company.
Right.
And you ask them a complex question about user preferences.
Right, something that takes some real digging.
Exactly. And they do a fantastic job. They read through everything, they find the patterns, give you a perfect answer. But now imagine that immediately after they hand you that report, you ask them a second, slightly different question about that exact same database.
And let me guess, they just stare at you blankly.
Total amnesia. They look at you and they have completely forgotten the database, how it's organized, what the main themes are, where to find literally anything. They have to start completely from scratch, reading all 50,000 entries again.
Which is, sadly, exactly how modern large language model agents operate today.
It's crazy, right?
It is. It's what we call the Goldfish memory problem.
Right?
Every single time they interact with a massive recurring document, they just treat it like it's the very first time they've ever seen it.
Right.
And that burns through time, it burns through compute costs, and it severely limits how smart the AI can actually be over a long workflow.
And that is exactly what we are going to fix today. We're going to look at how the researchers behind Peak created this persistent scratch pad for AI agents, effectively curing that goldfish memory.
Cheering it for good, hopefully.
But before we get to the cure, we really have to understand the disease. Why do our current best methods fail so spectacularly when an agent has to read the same massive document over and over?
Well, to understand the failure, we kind of need to map out the current landscape of how researchers have actually tried to give AI agents memory.
Okay, so what does that look like?
Think of the research space as a grid, like a four-square matrix. On the vertical axis, you have active memory methods versus passive memory methods.
Got it. Active and passive.
Right. And then on the horizontal axis, you have methods that focus on the agent or the task versus methods that focus on the external context.
Meaning the actual document you wanted to read.
Exactly, the document itself.
Okay, let's unpack this. A passive method would be something that just happens automatically in the background as a byproduct of the system running, right? Like keeping a chat history.
That is a perfect example, actually.
Yeah.
In the matrix, a passive method focused on the agent is what the researchers call the shared chat baseline.
Shared chat. Okay.
Yeah. The system just keeps appending the agent's prior actions and thoughts into the current context window. The idea is, the agent can look back at what it did previously and learn from it.
Makes sense in theory.
In theory, sure.
Yeah.
But the researchers found this rapidly accumulates into just a noisy, massive mess. Because every time the AI thinks, searches, or reads, all that text gets logged.
And we're talking about really long, complex tasks here. So how bad does that bloat actually get?
Oh, it gets catastrophic. The paper highlights an experiment using the Oolong benchmark.
Which is a tough one, right?
Very rigorous test for long context reasoning. Using that shared chat method, the agent's context ballooned so much that it spent up to 748 iterations, essentially just reading its own chat logs.
Wait, 748 iterations. Just to clarify for anyone who might not be, deep in the weeds on API calls, an iteration is a full cycle, right?
Right. The AI reading the prompt, generating a thought, taking an action, waiting for a response.
Doing that 700 times just to remember what it already did sounds like a complete nightmare for processing speed.
It totally is. It becomes so bogged down trying to parse its own history that its actual performance degrades. So researchers tried passive methods focused on the external context instead.
Which brings us to ARG, right? Retrieval Augmented Generation.
Exactly. RAG is the classic passive external method.
Right, which literally everyone is using right now. You type a question, the system does a keyword search on the document, grabs the most relevant paragraphs, and just shoves them into the prompt.
Exactly. But notice that it's passive. RAG provides access to the raw material based on a search query, but it doesn't maintain a curated evolving understanding of the document itself.
It's just a fetch and retrieve mechanism.
Precisely. So, moving to the active side of our matrix, we have something called ACE, or Agentic Context Engineering.
Okay, ACE. I've heard of this one.
Yeah, ACE is currently considered the state-of-the-art for prompt learning. It actively curates task-level strategies.
Task level meaning how to do the job.
Right. Over time, it learns a playbook for how to execute a specific task better.
But hold on, if ACE is learning a strategy for the task, it still isn't learning about the document itself.
You nailed it.
Like, okay, let's unpack this. If the AI is trying to find a specific fact in a massive library, shared chat is just keeping a bloated diary of every single footstep it took.
Right.
RAG is using a keyword search to pull random books off the shelf. And ACE is actively learning a strategy for how to walk down the aisles more efficiently. But none of them are actually drawing a map of the library.
What's fascinating here is that you've just perfectly identified the missing quadrant in the entire research space.
Oh, really?
Yeah. We have active agent state, passive agent state, and passive external context state. What has been entirely missing until this paper is active external context state.
A map of the actual document.
Exactly. The AI desperately needs what the researchers call orientation knowledge.
Orientation knowledge. I like that term.
It needs to know what the library contains, how the wings are organized, where different kinds of evidence live, completely independent of whatever specific question you happen to be asking it today.
That orientation knowledge is exactly what the human analyst from our first example would build up organically. Like, after reading a few reports, you naturally build a mental table of contents.
Right. You don't even have to think about it.
Yeah, you just know intuitively that Chapter 3 has the financial data and Chapter 5 has all the legal disclaimers.
And that intuition is precisely what Peak engineers into the AI. By the way, Peak stands for Context Map as an orientation cache.
Ah, okay. That explains the acronym.
And it solves this whole issue by creating a highly structured context map. Now, it's crucial to understand this isn't some massive external database.
Okay, so what is it then?
It is a small, constant-size artifact. Think of it like an ultra-fast hardware cache in a computer processor. It sits directly inside the agent system prompt.
Oh, wow. Inside the prompt itself.
Yes. It is a literal peek into the external context that persists across different tasks on the exact same document.
Okay, so we are putting a persistent map right into the prompt. But tokens are expensive and context windows have limits. How big is this map?
The researchers put it on a really strict budget of 224 tokens.
Wait, only 124?
Yeah. To put that in perspective for you, 224 tokens is roughly 750 words. It's about 2 pages of text.
That's tiny compared to a 50,000 entry database. So what does this highly compressed 2-page map actually look like? Because the paper breaks it down into specific sections, right?
It does. By default, every context map has 2 vital sections. First is the context roadmap.
The roadmap.
This is a high-level index of what the text contains and where to find it. For example, I might say this document contains 388 employee records, and they are formatted chronologically with a date, a user ID, and a performance score.
It's a really clean index. And what's the second section?
Second is the context understanding section. This captures the high-level themes, key entities, and how those entities actually relate to each other across the entire document.
Got it. And there are optional sections too, right? Things that adapt based on what the AI is actually doing.
Yes, 3 optional sections. The first is reusable results.
What goes in there?
So if the AI does a really complex, token-heavy, computation-like counting, exactly how many times a specific UI complaint appears in those 50K reviews, it saves that final number right here.
Oh, that's smart. That way it never has to do the math twice.
Exactly. Then you have domain constants for exact values or jargon that keep popping up. And finally, a parsing schema.
A parsing schema, like
Yeah.
formatting rules.
Yeah. The schema tells the AI exactly how the raw text is formatted, down to which specific delimiters or brackets are used, so the agent doesn't write a script that breaks just because of some silly formatting error.
So what does this all mean in practice? Let me play devil's advocate for a second here.
Sure, go ahead.
If I'm using an AI to analyze my company's massive internal wiki, is this context map just a really good text summary?
Yeah.
Because if so, why not just ask the AI to summarize the 50,000 customer reviews into a 2-page document and just keep that static summary in the prompt?
That is a really fundamental distinction to make. A summary condenses the actual content of the text.
Right.
It tries to squeeze as much raw information into a smaller space as possible.
Yeah, that's what a summary is.
But orientation knowledge, which is what the context map holds, curates the meaning and the structure. It is an evolving index. It is not a static book report.
Oh, I see.
If you summarize a library, you lose all the nuanced details in the individual books. If you build a structural map of the library, you still have access to every single detail in every single book. You just know exactly where to go to retrieve it instantly.
That makes total sense. It's structural grounding. But here's the catch. A map is totally useless if it's out of date or if it's drawn poorly.
Very true.
And no human engineer is going to sit there and manually update a 1024 token map for the AI every single time the AI reads a new document. So how is Peak building this thing automatically?
This brings us under the hood of the Peak system to what they call the programmable cache policy.
Sounds intense.
Over the first few queries the AI runs on a new document, the map is automatically updated using a three-part machine. And the truly brilliant part is that it doesn't need humans to provide ground truth answers to learn from.
No humans involved.
None. It builds the map purely based on the AI's inference-time execution trajectory.
Okay, let's translate that phrase. When they say inference-time execution trajectory, they basically mean the system is just watching the AI work, right?
That's a great way to put it, yeah.
It's observing the AI's internal monologue, the tool calls it makes, the dead ends it hits, and what it eventually figures out.
You've got it exactly. The system watches that messy trajectory and passes it to the first module of the machine, which is the distiller.
The distiller, okay.
The distiller basically analyzes the AI's execution log to diagnose what structural insights the agent stumbled upon during that run.
So it's looking for the aha moments.
Right. It looks at the current items in the map and tags them as helpful, harmful, neutral, or stale. Most importantly, it extracts new, transferable knowledge.
So if the AI spent 10 iterations aimlessly clicking around before realizing that all the Q3 financial data is actually hidden in Appendix B, the distiller flags that structural insight.
Yes. And crucially, it deliberately discards useless, one-off rules that won't help with a different question tomorrow.
Okay, so if we go back to our library metaphor, the distiller is the explorer out in the jungle. They are hacking through the vines, hitting dead ends, taking messy field notes, and figuring out where the river actually is.
And those field notes get passed to the second module, which is the cartographer.
Ah, making the actual map.
Exactly. The cartographer takes the distiller's raw diagnosis and translates it into structured, highly rigid edits for the context map.
Rigid edits like what?
It specifically issues add, replace, or delete commands. It keeps the map incredibly tidy by assigning unique identification numbers to every single entry.
Oh, which allows it to deduplicate information, right?
Spot on. It essentially standardizes the explorer's messy notes into a clean, readable map.
But wait, if the explorer keeps finding new things and the cartographer keeps adding them to the map, aren't we going to blow right past that 1024 token budget?
That's the danger, yeah.
Putting all this reusable data in the prompt sounds exactly like the bloat problem we had with the shared chat baseline.
And that is exactly why they built the third module. The evictor.
The evictor, I love these names.
Right. The evictor is the ruthless editor standing over the cartographer's shoulder, enforcing that strict 1024 token limit.
So what happens when they hit the limit?
If the cartographer's new additions push the map over the budget, the evictor steps in using a priority-based system.
What gets cut first?
It will delete parsing schemas and reusable results first, because those are kind of just nice-to-have conveniences. It will protect the crucial context roadmap and context understanding sections until the very end.
Ensuring the AI never loses its fundamental orientation.
Exactly.
Here's where it gets really interesting. We have a dedicated cartography team living inside the system. The distiller explores and diagnoses, the cartographer drafts the structured map, and the evictor mercilessly cuts it down to fit on one piece of paper.
It's a great system.
But I have to ask, why do we need both an explorer and a drafter? Like, why separate the distiller and the cartographer? What happens if we fire the drafter, save a step of processing, and just let the distiller do a monolithic update all at once?
You mean just read the messy logs and rewrite the entire map in one shot?
Yeah, exactly. Just do it all at once.
The researchers actually anticipated that exact question, so they tested it. They ran an ablation study.
Which is where you strip away a piece of a system to see how much it breaks, right?
Yep. They combined the distiller and the cartographer into a single monolithic step. And the result? The AI's performance dropped by a massive 7.7%.
Wait, almost an 8% drop just from asking the AI to do the diagnosis and the editing at the same time? Why?
Because it turns out large language models have limits on their cognitive load, very similar to humans.
Oh, that's fascinating.
Separating the diagnosis from the editing is absolutely essential.
Right.
If you force the model to analyze a massive messy trajectory log and write a perfectly structured deduplicated map at the exact same time, its attention gets divided.
Right. If you force our jungle explorer to draw the final pristine map while they are still actively hacking through the vines and running from tigers, they are going to draw a terrible map.
The data backs that up completely.
Yeah.
When they combined the steps, the researchers saw non-contextual facts start leaking into the map.
Oh, so it just got confused.
Yeah, the updates became noisy, duplicative, and the system became prone to accidentally overwriting stable, important entries just because it lost track of what it was doing.
Wow.
By separating them, the distiller can focus entirely on understanding the environment, and the cartographer can focus entirely on structure and deduplication.
That is a wild insight into how we really have to engineer around the psychology of these models.
Oh,
Okay, so the theory is incredibly elegant. The three-part machine of distiller, cartographer, and a victor makes logical sense.
it really does.
But does it actually work in the real world? We need to move from the theory to the hard data. Does peak actually outperform things like ACE, the previous state of the art?
The results are, frankly, dramatic. They tested peak on two major long-context benchmarks, Oolong and CL Bench.
And just to give you context, Oolong isn't a simple trivia test. It's a benchmark where the answer isn't in one place. It tests long context ruining and aggregation, forcing the AI to hunt for clues scattered across hundreds of pages to synthesize an answer.
Exactly. And peak absolutely crushes the strong baselines on these tasks.
Let's hear the numbers.
Okay, on the TrekQ course split of the Oolong benchmark, peak hit 58.1% accuracy. The state-of-the-art prompt learning framework, ACE, only hit 48.8%.
Wow, that is nearly a 10% absolute jump in accuracy.
And it gets better. On the Yahoo topic split, peak hit 57.0% compared to ACE's 42.0%.
That is a 15-point absolute increase.
Yeah, it's huge.
So it is drastically smarter at finding the needle in the haystack. But earlier we talked about efficiency, and that shared chat nightmare of 748 iterations. How does peak do on cost? Because running these massive models for enterprise tasks isn't cheap.
Peak is incredibly efficient because it eliminates the wandering. Remember, ACE tries to learn a task strategy, but it doesn't map the document. So the agent still wanders around the library aisle trying to find this specific book.
Right.
Peak gives the agent a map, so it walks straight to the exact shelf. As a result, Peak incurs 93 to 145 fewer iterations than ACE per task.
And since every iteration is an API call that costs compute credits?
Exactly. Peak incurs 1.7 to 5.8 times lower cost than ACE.
Yeah, only 6 times cheaper in some scenarios. That is staggering for any business trying to scale this.
The researchers noted that Peak consistently lies on the Pareto frontier for both cost and iterations.
The Pareto frontier, meaning the absolute optimal sweet spot, right?
Exactly. You literally cannot make the system any cheaper without severely hurting its accuracy. And you can't make it more accurate without making it far more expensive. It is structurally superior. And crucially, they proved this isn't just a fluke tied to one specific model's architecture.
Right, because sometimes a prompt trick only works on one specific version of one specific model.
They initially tested with a smaller model, GPT-5 Mini, but then they swapped in the massive frontier model, GPT-5.5, and the massive gains held up.
Oh, nice.
They swapped in an open source model, Qwen 3/4 Next, and it still worked. They even swapped out the entire backbone agent architecture and used OpenAI Codex, which is a production-grade coding agent, and Peak still delivered massive improvements.
That is huge for you, the listener. Like, if you are a developer building an AI tool or just a power user trying to get an AI to analyze your massive GitHub code repository or decades of corporate archives, Peak proves you don't need to spend massive amounts of money brute forcing the compute.
You really don't.
You don't need to force the AI to read its own chat logs 700 times. You just need to give your agent a map.
It fundamentally changes the economics of long-context AI workloads.
Okay, but as we know on this show, sometimes the most valuable insights come from the experiments that totally failed. The cutting room floor,
Ah, yes.
the ablations.
You mentioned the ablation study where combining the distiller and cartographer failed. What else did they try that didn't work?
Well, the failed experiments are illuminating because they show us what the AI actually values. The researchers naturally wondered, do we really need this complex machine? What else could we put in this 1024 token prompt to ground the AI?
Did they try just giving it the start of the document?
Yeah. The simplest idea was just to take the first 1024 tokens of the raw document, essentially the introduction, and slap it in the prompt. Barely helped at all. Just a 0.73% improvement.
Which makes sense. I mean, the introduction of a 50,000-word corporate document rarely contains a perfectly structured index of where the legal disclaimers are hidden on page 400. True. They also tried a retrieval playbook-style update, where they treated the context map like a tiny database to pull from using keyword matching, rather than keeping it constantly visible on the prompt.
Did that work?
That also barely helped. But the most fascinating failure of all was an experiment they called runtime feedback.
Oh, this is the one that really shocked me when I read the paper.
Right. The researchers thought, what if we have a separate LLM, actively read the agent's trajectory mid-task, and write natural language feedback to replace the map on the fly?
Basically, having a coach actively monitoring the AI.
Exactly.
Yep.
Updating the map in real time and telling it what to do while it's working. They hoped this active real-time coaching would keep the AI perfectly on track.
But it was a total disaster.
Performance tanked by a massive negative 14.86%.
Wait, I have to stop you there. Actively coaching the AI while it works actually makes it significantly worse, almost 15% worse.
Yep.
Why would giving it active real-time feedback destroy its ability to do the task?
Well, if we connect this to the bigger picture of how agents plan, it makes perfect sense. Overwriting the map at every single step destroys the AI's stable orientation.
Ah, I see.
You are polluting the AI's working memory with reactive, noisy commentary. It totally destabilizes its ability to plan a multi-step reasoning chain.
That's incredible.
It proves that AI agents, much like humans, need stable structural grounding to do complex work. They don't need someone yelling in their ear while they try to think.
It's the backseat driver effect. If our jungle explorer is trying to read the map and navigate a dangerous cliff, and the GPS voice keeps recalculating and yelling new instructions every 3 seconds, they're going to walk right off the edge.
Exactly.
They just need a stable map that doesn't change while they're walking.
That's exactly the dynamic. If the environment is constantly shifting beneath its feet because the system prompt is being overwritten with real-time coaching, the agent loses the thread. The context map only works because it provides a stable, global view, and it only updates between tasks, never during them. It allows the agent to execute its reasoning chain with confidence.
Okay, so to summarize the incredible journey of this deep dive, the era of AI agents treating every single interaction with a massive document like their very first time is coming to an end. The Goldfish memory is curable.
It really is.
By using a system like Peak to build a persistent, strictly budgeted context map, relying on that brilliant 3-part machine of the distiller to explore, the cartographer to draft, and the evictor to ruthlessly egg agents become drastically cheaper, faster, and more accurate.
Absolutely.
They stop wandering blindly down the library aisles, and they start navigating with a map.
And this raises an important question, one that the paper points toward but leaves for the future.
Ooh, what's that?
Right now, Peak builds a tiny 2024 token map for one agent reading one specific corpus of data. But what happens when agents start sharing these tiny, highly optimized orientation maps with each other?
Oh, wow. I hadn't even thought about the network effects of that.
Think about the implications. Could a massive server farm of AI agents map the structural orientation of the entire internet over the entirety of human case law or every medical journal ever published?
My mind is blown right now.
And then, could they hand that perfectly distilled 2-page orientation map to your personal laptop's AI in an instant? What happens when orientation knowledge, not just the raw data, but the structural understanding of how to navigate that data, becomes infinitely copyable and instantly shareable across billions of agents?
That is a mind-bending thought to leave on. We go from fixing one amnesiac data analyst to creating a global network of experts who instantly know the layout of every single library on Earth the moment they boot up.
Exactly.
We've cured the Goldfish memory, and now the AI has a permanent map of the world. Thank you so much for joining us on this deep dive. Keep exploring, keep questioning, and we will catch you on the next one.